Welcome to Gradient Daily, where we deep dive into an AI research paper every day. Today, we are meticulously deconstructing an absolute landmark in the field of computer vision. We are talking about a true paradigm shift here. We're looking at the groundbreaking ECCV 2020 paper by Ben Mildenhall, Pratul P. Srinivasan, Matthew Tansik, Jonathan T. Barron, Rabi Ramamurthy, and Ren Ni. This paper, titled NeRF, representing scenes as neural radiance fields for view synthesis, completely revolutionized how we approach rendering, visual style, and view synthesis. To understand the real-world impact right out of the gate, imagine you're just taking a few photos of a product with your everyday smartphone, or maybe you're flying a drone to capture a sweeping landscape. Now imagine instantly generating a Hollywood-grade photorealistic 3D asset for virtual reality or e-commerce that you can seamlessly view from literally any angle. No glitching, no weird artifacts, just pure visual perfection. This paper provides the foundational mathematics that made that a reality. Now, we aren't just going to skim the surface today. We are treating this as a rigorous graduate-level explainer. We're going to make sure you understand the profound conceptual leaps, the specific mathematical equations, and the brilliant architectural nuances the authors made to achieve this incredible visual style. So get comfortable, because we're going deep.
Okay, so here's our agenda for today's explainer. First, the view synthesis revolution. Second, demystifying 5D coordinates. Third, non-convolutional network architecture. Fourth, differentiable volume rendering. Fifth, photorealistic results and impact. And finally, number 6, future frontiers and limitations. Let's just jump right in. Section 1, the view synthesis revolution.
Let's pause for a second and really define this massive foundational term you're seeing: continuous volumetric scene function. To truly grasp why NeRF is such a massive leap forward, you really have to understand the old way of doing things, what it's replacing. Historically, in computer graphics and early neural rendering, if we wanted to represent a 3D object, let's say a highly detailed toy drum kit or an intricate flower, we used discrete structures. Think of voxels. Voxels are basically 3D pixels. Imagine building up your entire scene using tiny Lego bricks. Or think of point clouds, or those massive polygon meshes you see in video games. Well, the fatal mathematical flaw with all of these discrete structures is how their memory scales. It's a nightmare. If you want a voxel grid to look just twice as sharp, giving you exactly twice the resolution on the X, Y, and Z axes to get a better visual style, you actually have to multiply the memory footprint by 8. It scales cubically. Mathematically, that's big O of n cubed. You know what happens then? You quickly run out of GPU RAM before you ever even come close to reaching true fine-grained photorealism. Your computer just tops out. But a continuous volumetric scene function? That is completely different. Unlike a digital photograph made of tiny square pixels or a 3D model made of Lego-like voxels, a continuous volumetric scene function is an infinite, fluid mathematical space. Because it's a math function and not a rigid grid, there is absolutely no underlying resolution limit. None. You can mathematically query this space at any infinitely microscopic point and it will hold geometry and light data. It's a completely continuous representation. This effectively decouples the visual complexity of the scene from the memory footprint required to store it. You aren't storing billions of tiny cubes, you're just storing the parameters of a function. This theoretical leap is exactly what allows NeRF to render incredibly complex topologies and stunning visual styles without instantly crashing modern hardware. It's brilliant.
Section 2, demystifying 5B coordinates.
So, to query our continuous scene function, we need a coordinate system. We need an address. But 3 dimensions? 3 dimensions are simply not enough to capture reality. The paper introduces a 5D coordinate system, and this is absolutely crucial for achieving that photorealistic visual style. Let's break this down. Imagine a mosquito hovering in a room. The X, Y, and Z coordinates pinpoint exactly where that mosquito is floating in the air. That's your spatial location. But if we only asked our mathematical function, hey, what color is the light right at this specific XYZ location, we would be missing a massive piece of how reality actually works. Why? Because the color of a point in space often depends entirely on where you are looking from. Think about looking at a shiny object. Picture a classic record player, a freshly polished car hood, or just a calm body of water. If you take a step to your left, the reflection of the sun on the water moves, right? The specular highlight on that car hood shifts. The physical point in space hasn't changed its XYZ location one bit, but the color that reaches your eye has changed simply because your viewing direction has changed. In computer graphics and physics, these are known as non-Lambertinian effects. A Lambertinian surface is boring. It looks exactly the same from every angle. Think of matte chalk. But real-world scenes, the ones with incredible visual style, are heavily non-Lambertinian. They are full of complex specularity, glares, and reflections. This is exactly where the remaining two dimensions come into play, theta and phi. These specify the exact angle the virtual camera's eyes are looking from. By giving the neural network a 5D coordinate, basically saying, where are you and what angle are you looking from, the network is finally given the capability to understand and replicate complex view-dependent optical phenomena. Etch this into your mind. NeRF has to operate in a 5-dimensional coordinate space to fully master non-Lambertinian reality. That's the secret to the shine.
Section 3. Non-Convolutional Network Architecture.
For the past decade or so, convolutional neural networks, or CNNs, have pretty much dominated computer vision. They're everywhere. CNNs are absolutely brilliant at looking at grids, like a standard 2D grid of pixels in a photograph, and understanding local patterns by sliding a filter over neighboring pixels. But remember what we just talked about on the previous slide? We aren't dealing with a grid anymore. We are dealing with an infinite continuous 5D mathematical space. There are literally no neighboring pixels to convolve over in a single continuous coordinate query. It just doesn't apply. Therefore, instead of using a standard convolutional neural network, NeRF completely abandons them. It uses a pure, fully connected deep network, which is often called a multi-layer perceptron, or an MLP. However, there is a critical missing piece of the puzzle here that we absolutely must address for a true graduate-level understanding. If you just take raw 5D coordinates, just the simple numbers, and feed them directly into an MLP, the resulting 3D renders look absolutely terrible. I mean, they are completely blurry, washed out, and they lack any fine detail. It ruins the visual style entirely. Why does this happen? Well, research has proven that standard neural networks suffer from something called a spectral bias. Basically, they are heavily biased toward learning low-frequency functions and smoothly varying colors. They mathematically struggle to learn high-frequency details. Think about the sharp, jagged edge of a fern leaf or the incredibly fine lines of text on a computer screen. A raw MLP just blurs it all together like a bad watercolor painting. To solve this, the authors introduce a massive breakthrough step called positional encoding. Before the x, y, z, theta, and phi coordinates ever even touch the neural network, they are mathematically mapped into a much higher dimensional space. How? By using high-frequency sine and cosine functions. It's kind of like an audio equalizer, but for geometry. By transforming the simple spatial coordinates into a complex array of high-frequency waves, they literally force the network to pay attention to the microscopic, high-frequency changes in the geometry. This positional encoding is the absolute secret sauce that allows the MLP to learn razor-sharp details rather than blurry blobs. It is a brilliant, elegant workaround to the fundamental limitations of how fully connected networks perceive input data.
Over the next several minutes, we are going to deeply analyze this exact 4-step pipeline. We're going to trace the journey of a single ray of mathematical light as it travels from our virtual camera straight through the continuous scene to calculate density and color. Let's break down this pipeline exactly as the authors laid it out. Step 1. Query 5D coordinates along camera rays. I want you to imagine placing a virtual camera in perfectly empty space. From every single pixel on that camera sensor, we shoot a mathematical laser beam, a ray, straight out into the virtual world. As that ray travels forward through space, we sample discrete, specific points along that line. For every single one of those microscopic points, we record its XYZ location and the theta-phi angle of the ray itself. Step 2. We take all of those positionally encoded 5D coordinates. Remember, we just boosted them with sine and cosine waves, and we feed them one by one into our fully connected deep network. In the paper, you'll see this denoted mathematically as f sub theta, meaning it's a function parameterized by neural network weights, which they call theta. Step 3 is what actually comes out of the network. This is the output. The MLP outputs exactly two things for every single 5D coordinate: a volume density, which we call sigma, and a view-dependent emitted radiance, which is, for all intents and purposes, an RGB color. Density tells us how opaque that specific point in space is. Is it just empty air, or have we hit solid plastic? The RGB tells us the exact color of the light shining outward from that point. Finally, step 4, project into an image. We have all these thousands of densities and colors scattered along our invisible ray, but our screen is only 2D. We have to squash them all together mathematically to figure out the final accurate photorealistic color of that single solitary pixel on our camera sensor.
Let's zoom in and look a little closer at step 3, because understanding this concept of view-dependent emitted radiance is absolutely essential to why NeRF looks so good. To ensure the network learns this correctly without hallucinating weird artifacts, the authors did something structurally brilliant with the MLP's internal architecture. Remember that our ultimate goal is to render solid objects that also have realistic reflections. To do this, they don't just dump all 5 encoded coordinates in at the very beginning of the network. No. First, they feed only the 3D spatial coordinates, just the XYZ, into the network to predict the volume density, sigma. Why do this? It physically forces the network to understand that the geometry of an object, whether a point in space is solid wood or empty air,
cannot possibly change just because you look at it from a different angle. A wooden table is physically solid no matter where you stand in the room, right? Its density is a fixed physical property. Only after calculating that density, deep within the final layers of the network, does the architecture finally inject the viewing direction, theta and phi, to predict the final RGB color. This architectural separation is absolute genius. It ensures that the 3D geometry remains incredibly stable, solid, and completely independent of the camera's location, while the color is allowed to shift and shimmer depending on the angle from which it is observed. Think about it. If the authors hadn't architected this strict separation, the network might get confused. It might try to explain away a bright, shifting glare on a glass window by creating a fake, floating, translucent white cloud of geometry hovering right in front of the window, rather than learning it as a surface reflection that correctly depends on the viewing angle. This trick is a massive part of achieving that pristine visual style.
Section 4. Differentiable volume rendering.
All right, so we have our neural network outputting density and light for thousands of microscopic points along a ray, but we still have a problem. We must cross the bridge from this abstract 3D math back into a beautiful, viewable 2D image on our monitors. To achieve this projection, the authors resurrect continuous equations from classic computer graphics, specifically volume rendering. Look closely at the integral equation prominently displayed here. Don't be intimidated by the calculus. It's actually incredibly intuitive when you break it down. This is how we calculate the expected color, big C of R, of our camera ray, R. We take an integral from the near bound of the camera, Tn, to the far bound, Tf, basically from right in front of the lens to as far as the eye can see. Think of this entire process like shining a bright flashlight through a dark room filled with dense, colored smoke. Inside the integral, we have three critical variables being multiplied together for every single microscopic point along the ray. First is sigma of R of T. This is the volume density. In our analogy, this is exactly how thick the smoke is at that exact microscopic point in space. Second is little c of R of T, d. This is the emitted RGB color at that exact point, given our specific viewing direction, d. That's the color of the smoke particle. But the real magic here is the first term, T of T. This is the accumulated transmittance. Mathematically, transmittance represents the exact probability that the light travels from that point deep in the scene all the way back to the camera lens without hitting any other opaque particles along the way. Think about it. If the smoke is very thick early on in the ray, right near the camera, the transmittance drops to 0. That means any colors deeper into the scene are completely occluded. They are blocked from the camera's view. Classic volume rendering calculates exactly how much light reaches your eye by marching along the ray and accumulating these three values, density, color, and transmittance probability, for every microscopic particle. It's an incredibly elegant, physically grounded way to compress a vast 3D field of light into a single, perfectly colored 2D pixel.
And this brings us to what I think is the true stroke of genius in this paper, the realization that volume rendering is naturally differentiable. Now, why does this matter so much? It matters because differentiability is literally the absolute lifeblood of modern machine learning. In this case, classical calculus finally swoops in to save the day for graphic designers and AI researchers alike. Let me explain. In traditional computer graphics, rendering is very often a discrete binary process. A triangle or a polygon either covers a pixel or it doesn't. It's a harsh yes or no. Mathematically, you cannot take the derivative of a harsh step function like that, which means you cannot use it to train an AI through backpropagation. It's a dead end. But volume rendering? Volume rendering is continuous, it's soft, it's completely based on probabilities, opacities, and smooth integrals. Because the physics of this smoke rendering equation is naturally differentiable, we can use standard backpropagation to train the model. We shoot a virtual ray, we calculate a predicted pixel color using our fancy integral, and then we compare that predicted pixel to a real pixel from one of our actual input photographs. We calculate the mathematical error. Let's say, for example, our predicted pixel came out slightly too red compared to the real photo. Because the entire pipeline from the 2D image back through the 3D volume rendering integral all the way deep into the fully connected network is strictly differentiable, we can mathematically trace our errors backward. We can literally tell the network, hey, you need to decrease the red output at this specific spatial coordinate by exactly this much to fix the error. This incredibly smooth gradient allows us to train the entire massive neural network from scratch using nothing but the final 2D images as ground truth. It's almost like magic, but it's just really good math.
Section 5. Photorealistic Results and Impact.
Armed with this strictly differentiable end-to-end pipeline, let's explore exactly what inputs are needed to actually achieve these state-of-the-art results, and what those results mean for the industry's visual style moving forward. What I personally find most staggering about this paper is how remarkably little it asks for. To optimize this incredibly complex, continuous mathematical representation of an entire scene, you do not need an expensive, cumbersome LiDAR scanner. You do not need a highly paid technical artist to painstakingly craft a 3D mesh by hand or set up complex bounding boxes and lighting rigs. The only physical inputs required to train a NeRF are a sparse set of standard 2D photographs of a static scene. We're talking maybe 20 to 100 regular images taken from different angles. Along with those photos, you just need the precise mathematical location, which we call the camera pose, where each photo was taken. By camera pose, I mean the exact 3D coordinates in space, plus the rotational orientation of the camera lens for every single snapshot. You literally just feed the network a photo, tell it exactly where the camera was standing when it took that photo, and you let the differentiable volume rendering pipeline do the rest of the heavy lifting. The optimization technique used here is beautifully simple. The network aggressively minimizes the total squared error between the rendered pixel color it guesses and the true camera pixel color from the photograph. It iterates over this loss function thousands and thousands of times. Once it's fully trained, you can place your virtual camera anywhere in that continuous space, even in places where no input photo was ever physically taken, and the network will synthesize an entirely novel, geometrically flawless view. The implications for VR and 3D modeling are just staggering.
Let's rigorously compare this to prior work to truly contextualize the leap forward this represents. Before NeRF came along, the absolute state-of-the-art in neural rendering relied heavily on those discrete methods we talked about earlier. Researchers would try to push convolutional neural networks to generate voxel grids or stacked multiplane images. But as we discussed with that big O complexity nightmare, discrete convolutional methods are fundamentally bottlenecked by grid resolution and memory limits. If you want to render a truly sharp edge on a leaf to get that photorealistic visual style, you need an incredibly tiny voxel, which means your grid needs to be massive, which instantly blows up your GPU memory. Because of this, those older traditional methods would frequently result in scenes that look blurry, blocky, or they suffered from terrible ghosting artifacts, where the network simply couldn't squeeze enough high-frequency detail into the discrete grid. On the other hand, NeRF's continuous function bypasses this bottleneck entirely. The resolution of a NeRF is realistically only limited by the capacity of the multilayer perceptron itself. The memory footprint? It's just the weights of the neural network, typically just a few megabytes, regardless of how insanely complex the spatial geometry actually is. This allows for infinitely high visual resolution upon querying, and it gracefully handles incredibly complex geometry without breaking a sweat.
Now, to truly understand the impact of this paper, we must examine the specific datasets and metrics the authors used to prove their dominance. They didn't just test this on simple geometric primitives like cubes and spheres. They benchmarked NeRF on incredibly rigorous datasets to prove it could handle world-class visual style. First, they used the synthetic NeRF dataset. This contains highly complex, procedurally generated objects, like a fully rigged ship with microscopic ropes or a highly specular, shiny Lego bulldozer. This dataset provided perfectly exact camera poses over a full 360-degree hemisphere. This allowed them to test whether the network could learn perfect, crisp geometry and handle aggressive, non-Lambertian specularity without any noise in the camera data messing things up. Second, to prove it actually works in the messy real world, they used the LLFF dataset, or Local Light Field Fusion. These are real-world, complex, forward-facing scenes captured simply by walking around with a handheld smartphone. These scenes feature incredibly tricky things like delicate, translucent flower petals and highly reflective, transparent glass. When evaluated, NeRF absolutely shattered the existing benchmarks. They measured this using two key metrics. First, PSNR, or peak signal-to-noise ratio, which mathematically calculates pixel-by-pixel accuracy measured in decibels. Higher is better. Second, LPIPS. LPIPS is a fascinating metric that measures perceptual, structural similarity by actually using another neural network to judge how real an image looks to human eyes. NeRF beat the prior state-of-the-art across all these metrics by significant, incredibly wide margins. And here is a huge reason why. Because there is a single, underlying, unified 3D mathematical function generating the entire scene, objects don't flicker or warp impossibly as the camera moves around them. That temporal inconsistency was a massive problem in earlier, purely 2D image-to-image translation models, and NeRF completely solved it, resulting in a flawless visual style.
Section 6. Future Frontiers and Limitations.
However, as with any rigorous, PhD-level explainer, we cannot just marvel at the successes. We must critically interrogate the assumptions made by the authors to understand the true boundaries and limitations of this foundational technology. Where does it break? We must ask ourselves about the fragility of one very specific assumption, the absolute requirement of perfectly known camera poses. In the real-world LLFF dataset, these poses are derived using structure from motion software like Colmap. But in a true, real-world scenario, out in the wild, maybe with a shaky hand, mathematically perfect poses are incredibly difficult to capture reliably. Think about what happens if your pose estimation software is off by even a fraction of a degree, or just a few millimeters in space. The camera rays you shoot during training will not intersect correctly at the physical object. The network will receive directly conflicting information. One ray will tell it a specific point in space is a bright red petal, an intersecting ray from a slightly misaligned camera will tell it that the exact same point is empty white background wall. How does the network compromise? It blurs the geometry. This results in a hazy, degraded rendering that completely ruins that crisp visual style we were aiming for. Furthermore, Colmap notoriously fails on textureless surfaces. If you have a blank white wall or a highly reflective mirror, Colmap gets confused, making it nearly impossible to get accurate poses in those environments. If the poses are garbage, the NeRF will be garbage. Another massive limitation of the original 2020 NeRF paper is the incredibly harsh inference time constraints. Because the network has to query the MLP hundreds of times along a single ray just to render one pixel, rendering a full 1080p high-definition image requires millions upon millions of network passes. At the time of publication, rendering a single image took seconds to minutes. That makes real-time, 60 frames per second interactive rendering completely impossible with this vanilla architecture.
To conclude this graduate-level explainer, here are your 3 memorable takeaways summarizing the sheer, absolute brilliance of this paper. First, NeRF redefines scenes not as discrete grids or voxels, but as continuous 5-dimensional mathematical functions, brilliantly utilizing positional encoding to capture the high-frequency detail necessary for true photorealism. Second, it completely abandons standard convolutional architecture, relying instead on a non-convolutional multilayer perceptron to act as a universal approximator for both density and view-dependent color. And third, by resurrecting classic differentiable volume rendering equations, the authors prove beyond a shadow of a doubt that we can train this incredibly complex 3D representation end-to-end using absolutely nothing but standard 2D photographs. If you enjoyed this rigorous deep dive, please smash the like and subscribe buttons right now. Hit that notification bell so you don't miss our next analysis, and definitely check back tomorrow for another Gradient Daily paper deep dive. I want to leave you with a final provocative thought. If a simple 5D neural network can perfectly hallucinate an entire photorealistic reality from just a handful of 2D photos, it begs the question, are we moving toward a future where traditional 3D modeled graphics engines are entirely replaced by learned continuous light fields? And if a neural network can generate a perfectly photorealistic world from scratch with such stunning visual style, how will we ever truly trust what our eyes see on a screen again? Keep learning, and I will see you in the next explainer.